problem was the least squares problem, right? So the problem that we had seen was least squares problem, and the problem that we were looking at was ax is equal to b. So a and b are given. A and b are given, and you want to find out x, right? Find x. So there were several issues that were there. So the first thing was that can you solve this problem exactly? So find x meaning find x such that ax is equal to b. So there exists an exact solution. If the exact solution does not exist, then you try to minimize this particular problem, right? Ax minus b, it's 2 now, right? So that is what you want to minimize for all possible values of x. So if not exact solution, then next best thing, like the closest linear span to b. That's what you are trying to find out, right? So this is the problem that you have. But now the question is, so typically what we had looked at was in this least squares problem, the existence on uniqueness of the solution and so on and so forth. All these things were subject to the fact that A was a matrix which was of the size m by n, and we had assumed that m is strictly greater than or equal to n, right? So either you have a square matrix or you have a matrix which has more rows than columns, right? So typically the matrix A looks like this. And what was the other condition? The other condition was that the columns of A are linearly independent, right? So these are the two conditions. These are the two conditions that we had looked at. So the first condition was this, second condition was this. So the case when m is actually equal to n, you have a square invertible matrix, and then the least squares problem actually has exactly one solution. In fact, the exact solution to the problem x is equal to b, right? And if m is strictly greater than n, then you have more number of rows than columns, and then what we are really looking at is the least square solution, unique least square solution, right? So we had proved that this condition is equivalent to invertibility of Gram matrix, and then you can write down the least square solution in this particular case in terms of inverse of Gram matrix, right? We call that pseudo inverse. So I hope you remember all those things. So this is something that we had already done. We had discussed computationally efficient ways to construct the solutions and so on and so forth. But the problem that we did not look at, the problem that we did not cover. So for example, here the constraint was m is greater than or equal to n. But now if I have other constraint I have this particular problem, say ax is equal to b. Okay, so ax is equal to b is what I am really interested in looking at. And what I am having is that m is much smaller than n, right? M is much less than n. So typically the matrix A I am looking at is really like this. Okay, so typically a matrix A that I am looking at is really like this. One such problem we saw yesterday itself, right? So in yesterday's discussion itself, we saw this type of problem, right? So you were looking at this particular matrix AX is equal to B, right? Where A is a wide matrix. So this type of problem we saw yesterday. The matrix A really looks like this, and then you want to find out x such that ax is equal to b. Obviously, if there exists an exact solution, then there is no problem. But in this particular case, as we pointed out yesterday also, that this matrix A will have a non-trivial null space, right? So this matrix A will have non-trivial null space. Null space, or the word that if you have used kernel, then you understand this kernel, right? So what does this mean? The set n of all x n in, so suppose this is Rm cross n, then x in Rn such that a xn is equal to 0. N specifically, okay, to say that this is a null space vector. So if you want, I can like use capital N, x sub n, okay? X sub n. Okay, so it is a vector in the null space of A. So A into xn is equal to 0. Now suppose x in Rn is such that Ax is equal to b. Okay, so that means that x is the solution to this Ax is equal to b. Then obviously for every x n in this null space, x plus xn also is a solution. In other words, a into x plus xn will also be equal to b, because axn is equal to 0. So you add the null space vector to the particular solution. So this x is a particular solution. Then you add all the null space solutions to this particular solution, you will get solutions, right? So what does that mean? Because so if a solution exists, suppose x is, so if one particular solution exists, then obviously there are infinitely many solutions, right? So there are infinitely many solutions present. So the question is which solution to choose now. If there are infinitely many solutions to choose from, then which solution we would like to choose, right? So that is the question. That is the question that we want. And the obvious choice comes to the mind that we want least norm solution. Okay, least norm solution. So the least norm solution means that I want a solution x to this least squares problem such that the solution x hat, its norm is the least, right? So amongst all the solutions that I have, so for example, if there is only one linearly independent particular solution x, then you look at this particular solution space, right? So these are all the solutions to this problem x is equal to b. Amongst this set, you choose that vector x which will have the least norm, right? So singular value decomposition will again come to our rescue, and we can use SVD to actually construct the least norm solution in case when norm is 2. Okay, 2 norm is considered, that is what will happen. But in many real life applications, what really happens is that the solution that you seek, the solution x that you see may be required to be sparse solution. Okay, you want as many zero entries as possible in this solution x. Okay, so that is the objective. You want a sparse solution, and with that sparse solution, then you have something really amazing going on here, right? So this sparse solution is possibly easy to store and easy to transmit. So you want this sparse solution, and it can be reconstructed back to this B later on when you want to, right? So these are the type of things that are very useful. So like one choice is to minimize the norm, to norm, but another choice is might be that we want to seek the sparsest possible solution. Okay, the solution which is like as sparse as possible. Okay, so that is what we want. So a sparse solution is a solution. A sparse solution is a solution with many zeros, right? So instead of minimizing the norm, we may seek a solution like this. Okay, we may seek a sparse solution rather than minimizing this norm. And if you are really interested in doing that, then the type of problem that people solve is kind of compressive sensing problem. Okay, so this type of problem is termed in in the literature as compressive sensing. Okay, so what you are trying to do, you are trying to solve this Ax is equal to B problem. A is really a wide matrix, and you're trying to find out x such that Ax is equal to B. And not only you want any arbitrary x, because if the solution exists, exact solution, then there are infinitely many solutions, obviously, because of the non-trivial null space that this matrix is having. So you are trying to have certain constraint on x, right? So if you use pseudo inverse, the one that we have already used, you will get the least norm solution. Okay, so the pseudo inverse or the singular value decomposition will give you the least norm solution, the norm being 2 norm. But now what we want is we really want solution that is as sparse as possible. Okay, sparsity. So actually this type of problem can be called as basis pursuit problem. Okay, and what is it that you are doing? You are minimizing one norm of x. Okay, one norm of x, which is nothing but x1 plus x2 plus xn, right? You consider the components of x and they take their absolute sum, right? So x1 plus x2 plus xn, and the constraint that you have is the actually system of equations x is equal to b. That means that what is the feasible space? The feasible space is the all possible solutions x such that ax is equal to b. And what you're trying to find out, you're trying to find out that particular x, you're trying to find out that particular x, which will have the x which will have the least one norm. Okay, so that is what you really are interested in solving. So if you solve this particular problem, if you solve this particular problem, which is called as basis pursuit problem, then you get the least one norm solution. You do not get least two norm solution, but you get least one norm solution. And this least one norm solution actually kind of guarantees the sparsity. Okay, so the sparsity kind of is more forthcoming in this one norm minimization rather than finding out the least norm solution with respect to two norm. Okay, so this is what we really do. And then there is another thing. What is the another problem, similar problem? So the similar problem is called as lasso. So this problem lasso, mainly it is used in statistics. Okay, so a research group of statisticians from Stanford University, mainly Tipshirani. I think his book you might have seen, like machine learning book by Tipshirani, right? So that Tipshirani was basically the person who introduced this lasso, and what he really did was he said he wants to minimize this norm of ax minus b whole square. Okay, so this is what he wants to do. And the problem is that he will penalize the one norm. Okay, he will penalize the one norm. So this particular lambda is basically, this particular lambda here is basically the Lagrange multiplier. So the problem really that he's looking at is that minimize ax minus b whole square subject to the constraint that norm of x is less than or equal to some threshold t. Okay, so that is what the problem is. And when you apply Lagrange multipliers, you get this where you have penalization for the one norm of x. So these two problems, lasso is different slightly than this basis pursuit. So in basis pursuit, what is happening? You are seeking least norm solution. In lasso, by putting ax is equal to b rather than in the constraint in the cost function, what you are allowing for? You are allowing for having noise in matrices A and B, which is more realistic, right? In many real life situations where matrices A and B will be noisy, and you may not get the exact solution because of the noise terms. So that probably creates the problem in the constraint when you just have a hard constraint x is equal to b. So that you kind of avoid by looking at this particular thing, right? So norm x1 is less than or equal to t, right? So this is what you have, and that constraint, that t you can fix, that is your choice. So that's a threshold in the optimization problem. That's equivalently translated into the Lagrange multiplier lambda. And when you are trying to simulate and solve the problem, this lambda, which value of lambda you choose, and so on and so forth, right? So these are the type of things. So similar thing we have already seen. If you remember, in the least squares problem, if this were not equal to 1, but if this were equal to 2, we had really seen this problem. Do you remember this problem being discussed in the class when we had, instead of one norm as a constraint, two norm as a constraint? Do you remember this? We had several cost functions which were simultaneously being put together in the minimization. Do you remember that problem of optimization we had discussed in the class?
Yes, sir. The multi-objective.
Correct, multi-objective least squares problem. So we had discussed this multi-objective least squares problem. So this is kind of a little further generalization of the multi-objective least squares problem. But what is really happening? What is really happening is instead of two norm, now I am generalizing and I am kind of minimizing the one norm. Okay, so that's what I am doing. So this is the difference. Okay, so this is the problem setting. So what we really are doing? What we really are doing is that we are trying to find out the solution x to the ax is equal to b system of linear equations where A is really wide matrix. So you have less number of rows than columns. And what is the constraint? The constraint, this norm of x1, okay, the constraint is somehow saying that you will get sparse solution. Okay, you will get sparse solution. So that is what this problem is saying. So this is one of the important problems, very important problems. And you see this problem is central in many research areas. So in natural language processing, for example, this x actually has the meaning of sparse dictionary representation for the given word B, and A is actually the dictionary. So if you are given a dictionary, can you find out the sparse representation for the given word B using the dictionary? That is the problem that they try to understand in natural language processing. And similarly, many other fields in AI ML, they actually have this particular setting where you are actually trying to find out sparse solution. Okay, you are trying to find out a sparse solution. So if you are trying to find out sparse solution, then this is what you will do. So there are several things. The first thing is like why using one norm you kind of get sparsity. That's the first thing. And the second thing is, once you understand why you are getting sparsity, what are the type of algorithms that one might use. Okay, so both these things, why you will get sparsity with the help of one norm, and why will you how will you solve this particular optimization problem. I'm not going to go into much technical details. Once again, it's kind of hand waving, but this is the type of problem which is of current interest. Okay, a lot of work has been done, a lot of work in coming up with the different type of algorithms. Okay, so this is a very interesting problem. This is an important problem and area of active research. Okay, recently many people have worked in this, and this type of problems, these compressive sensing problems, they find a lot of applications in many AI ML. Okay, so this is something that is really very important problem. So I just wanted to draw your attention to this particular problem. And what really happens is that it kind of completes the story that we started with, right? So now when you are looking at Ax is equal to B, when you are looking at X, all possible cases of different sizes of A and all possible scenarios of solving this particular problem kind of get covered when we say these things. Okay, so basically this is an optimization problem, and if anybody is interested in going further in understanding optimization things, I think book written by Stephen Boyd, which is I think available online. This is the third book. I think it's called Foundations and Trends in Machine Learning, I think. So that book talks of very nice optimization algorithms that can be used to solve problems of this type. Okay, so Stephen Boyd, being a convex optimization person, wonderfully written this book. So I think so far I have mentioned three books by Stephen Boyd. One which we actually used, Introduction to Applied Linear Algebra and like least squares problems. So that was one book which is available online. The other book is Convex Optimization by Stephen Boyd. And the third book that I'm mentioning today is a different book, which is basically book on this optimization and learning via alternating minimization. Okay, so optimization and learning via alternating minimization, that comes in Foundations and Trends in Machine Learning. Okay, so this I think book is available online. I'm not sure, but you can check and you can see. So that book has very nice detailed survey of all the important methods. on solving problems of this type. Okay, so I'm not going into much detail obviously of those things, but as a pointer you can always look at that particular book. Okay, so this is the problem that we are trying to solve, and this particular thing, this particular lasso, okay, this one that is proposed by Tipsy Rani. So this one, why will it guarantee, or at least intuitively, why will it have like sparse solution possible, as opposed to, instead of one norm, if you took constraint on two norm, then that type of regression, why would it not work? Okay, so that intuition, of course, I want to give, though not the complete this thing. Okay, but before that, there is something that I want you to remember. There is something which is called as L0. Okay, so this L0, people call it L0 norm, but this is not really a norm. So what is this L0? So it is actually denoted at X sub 0. It's like notation of norm that they use, though it is not a norm. And what is this? This is the number of components which are non-zero. Okay, so number of components which are non-zero. So number of components which are non-zero is basically not norm, right? So I mean, why is it not norm? Because if I have vector x which is equal to 1, 0, 2, then what is x0? X0 is equal to 2. Now, if I have the vector 2 times x, which is 2, 0, 4, then this will also have, so this 2x will also be 2. But if it were norm, what should it be? It should be 4, right? So clearly this 0, the counting thing, right? The counting thing, number of components which are not 0. It's not a norm, but what we are really trying to do, we are trying to minimize this L0 norm, right? So we are trying to minimize the number of non-zero entries in the solution. That's what will mean to say that we are trying to sparsify. But this thing to start with is not a norm. Okay, so that's the problem. So when instead of minimizing this, you convexify the problem. So after convexifying, what you get is basically L1 norm. Okay, so after convexifying, what you really get is this one norm thing that is sitting over here. Okay, so please notice that here both the cost functions are convex, right? So both these basis pursuit or lasso, whichever formulation you want to look at, both these problems are actually convex optimization problems. And this convex, once the problem is convex optimization problem, you are guaranteed that there will exist local global minimum, and the only thing now is to come up with the numerically computationally best algorithm, fastest algorithm to compute that global minimum, right? So that's what people are really trying to do. So these problems are basically convex optimization problems, right? So if you consider this L0 norm in the optimization, then you are not actually solving a convex optimization problem. It becomes a highly nonlinear optimization problem. Nonlinear optimization problems are not easy to tackle in real life scenario. Okay, so that's the problem. So after convexification, so again, this is like lot of hand waving. These type of things require a lot of theoretical and technical background to be built. But at least you are aware of these things now when I'm mentioning them. Okay, so there are a lot of gaps in my explanation, but I suppose you also appreciate that these are the things which I just want to mention also. Okay, so for greater understanding and correct technical details, I think you should always refer to the books that I am saying. Okay. So after convexification, you get L1 norm rather than L0 norm. Okay. So that is what happens. And then you convert the non-convex problem into a convex optimization problem. What is the advantage? The advantage is that once you convert it to a convex optimization problem, you can find out the solution, global minimum, easily. But again, the solution that you find out is actually the approximate solution to the original problem that you really seek, right? So that is something that we have to live with. So that is what has happened. Yeah. Somebody was asking a doubt. Yeah.
Looking at the cost function, Can you just brief how can we make sure that this is convex and doesn't have multiple minimas?
This is a convex function, right? So basically what has happened, uh, this particular problem that you see here, this is actually the problem of the type minimum of f1 plus f2. Okay, I am adding two functions and these two functions individually are convex function. That is what I mean. So f1 is a convex function, f2 is a convex function. That's what I'm really meaning.
Okay, okay, sir.
Okay. So the convexity of f1 f2 is important because then when you go to this alternating minimization thing, in that alternating minimization thing, convexity of f1 and f2 really plays a key role. So that is what is going to happen. Okay, so that's how the numerical algorithms are designed. So in that context, I am saying f1 and f2 being convex help. Okay, so that's what is being looked at here. Okay, so this is what really happens. So this problem is a really important problem. This problem has a lot of real life applications. So now coming back to this thing of intuition. Okay, so intuitively, like, why do you think L1 norm is better in order to get approximations? Intuitively, can you tell? So in order to get to that intuition, first I want a quick understanding of optimization problems from you. Okay, so like you all have studied linear programming problem, right? So in 12th class, maybe possibly 11th class, I don't know when, you solve this linear programming problem using graphs, right? So in R2, you used to plot certain lines as constants and whatnot, and then you had solved this particular problem, right, using graphs, this linear programming problem. So can anybody tell me, uh, quickly tell me, how did you solve this problem graphically, just quickly? Can anybody say quickly?
Plot the constraints, then find out the intersection points, and it was guaranteed that the solution would lie on one of these intersection points, and then evaluate our function on these points and find the
Yeah,
maximum.
so
Maximum.
correct. So this is what you did. So you would construct the polytope, so to speak, or you will find out the region or feasible region, and it will be a convex polytope because it's a linear programming problem. And then you just check the solutions on the points, right, of this polygon. That's what you did. But why is guaranteed that the solution will always be on those polygons? Why is it guaranteed? Why is that guaranteed?
Sir, because like the constraints are lines and they represent an inequality. So the
Mhm.
maximum or the minimum of that inequality would lie on that line. Like basically, let's say x plus y is greater than 0. So we would draw x plus y and half of the graph would be like satisfying the constraint divided by the x plus y line. And whatever if we were trying to minimize, then also the inequality would be maximum at that line, and like maximum minimization would be also at that line.
Yeah, but why not inside that line? Like, why not inside the polygon region? Why only on the vertices? So less than or equal to inequality is guaranteed in the entire half plane, right?
Yes, sir.
Yeah, so why not inside the polygon? Why only on the vertices?
So sir, like basically, let's say there are three constraints and we choose, like it would form a triangle and we would choose one vertex. So now like we have three options, and all the three options are like they have two lying on the same line and one lying inside the half of the third constraint. So
Yeah.
like it would be satisfying the like exactly the constraint for two and like within the boundary for one. Like it would always lie for all the three on the same point.
Yeah, but why not inside the triangle? That's the question I'm asking.
Sir, I have a alternate explanation. So in linear programming problem, what we considered was that objective functions were also kind of linear and constraints are also linear. And now if you want to do, let's say, Lagrange, find the maximum minimum using Lagrange method, using constraints.
Yeah.
So you would say something like the constraint function plus lambda time the equation of that polygon, right? So now if you want to find maxima or minima, the either the derivative should be 0 or the derivative should not be defined. So in the polygon, if you see that in at only at the vertices there are sharp turns, so there the derivatives are not defined. So the at that position only, if you take
That does
the
not that does not mean that no, I don't really understand this, but
Sir, I have a geometrical interpretation.
okay.
Sir, in n dimension, let's consider n variables.
No, I am just saying in two dimensions.
Two variables. Okay, fine.
Yeah.
So in two variables, we have a feasible region, and our solution lies on that feasible region. Now, let's say we consider any point which is inside the feasible region, and it's not on its boundary. Then then in every direction around that feasible point, we can get to another point. So the problem with any point inside is that we can go along the direction along the objective function and increase or decrease our objective function as per minimization or maximization. So any point inside, from any point inside the feasible region, we can get to a better point. Hence, it cannot be the optimal.
So how will you move in the direction of minimum from inside to boundary?
So the equation of the objective function gives us a line and perpendicular to that line.
Correct. So correct. So basically what you're saying, I'll try to draw that now. Okay. So suppose this is the feasible region. Okay. Do you all agree that this might be a feasible region? Is that okay? This can be a feasible region. So this in the first quadrant. Okay. So this is the feasible region that we have. So these are the points, boundary points, okay, at which you will try to see what is really happening. Okay, these are the boundary points at which you will try to see what is happening. Now I'm trying to find out maximum or minimum. It doesn't matter. Okay, so whatever is the problem, minimum, maximum, whatever problem I'm trying to solve, it doesn't matter. I have a line ax1 plus bx2, right? So ax1 plus bx2. So this ax1 plus bx2, I'll consider to be a constant c. Okay, ax1 plus bx2 is equal to c. So ax1 plus bx2 equal to c will be some line. Do you all agree in this particular plane? For a fixed c, it will be a line. Is that okay? Do you all agree?
Yes.
So suppose that line is this. Okay, this is the line. ax1 plus bx2 is equal to c. This is the line. Okay. Now for different values of c, what will only happen to this line? The line will shift, right? So the line will shift. That's all will happen, right? So we'll have another line which is parallel to the line that I have drawn for different values of c. So this is like level surface of the cost function. So these different lines, so each value of c you get certain you get certain set on the R2 plane, that is called as level surface. Okay, so these are level surfaces of the cost function. Do you all agree? These are all level surfaces of the cost function. Different values of c will give you different lines. In this particular case, those lines are parallel. So now what do I do? I just move this line for various values of c. So this line is the one that I have. Then I will move this line and maybe I'll get this line. Maybe I'll get this line, maybe I'll get this line, maybe I'll get this line, and so on and so forth. So what am I getting? I am getting the pairs x1, x2 in the R2 plane. So any pair here I pick of x1, x2. This is the pair x1, x2 that I pick here. For this pair x1, x2, what is the value of the cost function? The value of the cost function is C. Here, what is the value of the cost function? The value of the cost function is still C. So entirely on this line, ax1 plus bx2 is equal to C. The value of the cost function is C. And now what do? You move this C for different values. What will happen? So when it intersects with this polygon, what will happen? It will first intersect with only a point. Do you agree? So suppose I am coming from this side with the different values of C. What is the first point of this polygon where this line will intersect? This is the point where this line will intersect first. So if I'm trying to find out minimum value of ax1 plus bx2, obviously it will be at this point in the origin. Because if I move slightly further, if I draw this particular line, then the value is greater than 0 for this line. Do you agree? Do you see geometrically how I'm getting at that particular point only? And if this cost function level surface actually becomes parallel to one of the constraints, then what happens? It intersects with entire side in one go. It intersects with entire side in one go, and that's it. Then you get the minimum as entire line segment, right? So geometrically, you can see what is really happening. Geometrically, you can see for a linear programming problem, why the solutions will always occur at the corner points, right? Or at best on the edges. Do you understand the geometry now? What I'm really doing? I'm building level surfaces and I'm seeing how those level surfaces really look like. Is that okay? Is that fine? And now you will ask me why I started talking of this level surfaces and these things. The reason why I started talking about level surfaces is this. So this particular thing in our lasso is minimization half of ax minus b whole square, right? So if you see this, then this is a convex function. This cost function is a convex function. And if you see the level surface of this cost function on this on this space where x belongs, if you see this, then it actually is like spherical. Okay, it is kind of circular shape, spherical shape. Okay, and what is happening? So this is our plane of this is our space of x. So the space of x I am just drawing in R2. So in R2, if you want to realize what will happen, because you are looking at one norm as constraint, so your one norm less than or equal to t will mean that you are looking at this particular set as your feasible set, right? So this is your feasible set given by the constraint. So this is the feasible set. So this is the feasible set. What is this feasible set? One norm is less than or equal to t, right? And this is the level surface. Level surface of half norm of ax minus b whole square. And now what is going to happen? What is really going to happen is with a very high probability. Okay, so what I will do, I'll start looking at the level surfaces. So the level surfaces will look like this. So these are the concentric level surfaces, and with very high probability, the chances are really very high. I'm not saying it will always happen, but with a high probability, this circle will intersect with the feasible region in one of the corners of this diamond. And if it intersects to one of the corners of this diamond, what really happens? What really happens is that in this point, you get kind of sparse solution, right? Why is it a sparse solution? It is a sparse solution because, can you tell why it's a sparse solution? Because one of the coordinates is 0, right? There one of the coordinates is 0. Now imagine this thing happening in a higher dimensional space. In a three-dimensional space, what you will have in a three-dimensional space, you will have generalization of this diamond, right? So you'll have all those different points on x, y, z axis, and you will join all those points and you will construct this generalization of this diamond into 3 dimensions. Then you will have those ellipsoids or spheres coming out as concentric ellipsoids or concentric these things as level surfaces. The chance is really very high that it will hit one of the corners, and if it really does, then you get sparsity, right? So that's why that L1 norm being present there kind of guarantees sparsity. This is very hand waving argument, but geometrically this is what is really happening. So if you understand the concept of level surface and how these level surfaces are moved in order to get the optimization, same thing is happening here. I have a level surface for the cost function and I'll play with these level surfaces. So what is really happening? What is really happening is on this entire circle, the cost function value is same. Then on this entire circle, the value of the cost function is same. It is more than this value. So you think of it as a kadai, right? You use in kitchen, right? So the kadai is a convex surface, right? So your cost function is looking like the kadai. And if you project, like if you see from the top of the kadai down, then what do you see? Down, if you project, like intersect it with XY plane, then you will get circles, different rings. Those rings you project down onto the XY plane. So you'll get the points on the XY plane for which the value of the function is height of that ring from the bottom, right? So that's what these level surfaces really are. So that's the geometry. So okay, so and then you have a diamond there, and you see when you start varying these level surfaces for different heights of kadai, how those level surfaces become concentric circles or concentric ellipses, so to speak, and the chance is really very high that they will intersect with the corners. Okay, I'm not saying every time they have to intersect with the corners, but chances are high that they will intersect with the corners or the edges. And then even if it like in a higher dimension, you kind of get many coordinates in x to be 0, and that's what is going to happen. Okay, so this is like rough geometrical intuition behind why if you have one norm, you will kind of have sparsity. This is hand waving, but if you think of any better explanation or want to add something to what I have said which will facilitate this, please feel free to discuss this. Anything that you would like to add here? So any of you have used this type of formulation, like compressive sensing type of application formulation in problems that you are trying to solve previously? Have you used any algorithms to solve these type of problems? Anybody has any experience doing this type of stuff? Okay, so this is all actually I wanted to say about this particular problem, compressive sensing problem. So once again, what is this problem? This problem is basically you're trying to solve Ax is equal to B, but now the case is that A is really a wide matrix. Okay, A is a wide matrix, and previous cases where A was square matrix and A is tall matrix, we had discussed in details those cases in the class. So the case of A is a wide matrix, A being a wide matrix, we have not discussed previously. So here I am just kind of introducing it, and I am just showing this to you. The optimization is the trick here, And the way you get sparsity, this is the geometrical kind of intuition behind why you would get sparsity. So I like tried my best to explain this intersection of level surfaces with this diamond. But if you like want like really very good explanation of this, I think you can look at the book by Tibshirani. Okay, so Tibshirani was the one who proposed this lasso thing. So Tibshirani's book. There are two books I think by Tibshirani. So the second book, the sparse learning book. Okay, so the sparse learning or sparse model, something like that. I don't remember the title, but the book is by Springer. Okay, so I think we all have free access to Springer books, so you may get this book online. So in this book, it's not a very big book, only probably 200 250 pages or something like that, and very interesting problems are discussed in that book. So in the first chapter of this book, sparse learning, probably page 10 12, I don't know. So on that page, this explanation is very nicely given. So Tibshirani's book, this explanation is very nicely given about how sparsity actually comes because of this L1 norm. So this is the explanation I have like read and understood from that book. I have tried to do that. So probably if you do not understand what I'm saying, you can go to this book directly and see from this book what I'm really trying to say. Okay, so this is one reference where you can actually find out the discussion about how sparsity is induced because of this one, okay, feasible set. So this is something that you can look into. So this was about everything that I had in my mind about matrices and matrix decompositions that I wanted to cover so far in this particular course. Okay, so the plan is in the next week, like 2-3 lectures, whatever we will get, I will try to say few things about tensors. Okay, so tensors are also really very important. So that is what I wanted to say. So before we stop today, I don't want to start a new topic today. So before we start, if you have anything to say about things like any specific topic that you would like to see rather than tensors, if I am like able to do it, I'll try to do it in the next week. So, or otherwise we'll stop here today and next week we'll continue with those things. And next Friday we have exam. Okay, so next Friday is exam day. Next Friday we'll have exam, last exam for this course. Yeah, Kaushik.
Yeah, sir, previously we had mentioned that after the SVD is introduced, you will kind of revisit the the inverse of a matrix and connect it to the SVD. So that I think Professor Mitra has also done it but it will also be good if you kind of take us through, if possible.
Okay, that can be done in 5-10 minutes. I can do that. I can do that. No problem. So suppose A is a matrix whose singular value decomposition is U sigma V transpose. So basically you have U matrix, then you have sigma 1, sigma 2 up to sigma R, then zeros here, here, based on rank of the matrix. So rank of matrix is R, then you get this particular type. Okay, and then the sizes of U sigma V are appropriate, which are like matching with the size of A. Okay, so for the time being, let us assume that A is a square matrix. So let A be a matrix of size n cross n. Also, let us assume that A is invertible. Okay. Also assume that A is invertible. Then suppose U sigma V transpose, so sigma 1 up to sigma n. Because A is invertible, the rank of the matrix is n. So there are n non-zero singular values of A, and U sigma V transpose, this is how your matrix look like. And now if I want to take inverse of A, I am allowed to take, because A is a invertible matrix. I'll have this U sigma 1 up to sigma n V transpose inverse, right? The inverse on the right hand side. So I'll use the properties of inverse. So I have V transpose inverse. Then the inverse of this diagonal matrix, right? So if you agree, the inverse of this diagonal matrix is basically 1 upon sigma 1, 1 upon sigma 2, 1 upon sigma n, all these zeros, and then you have U inverse. Is that okay? That's what you will get. But now what this V transpose inverse is, we know that V is an orthogonal matrix. So inverse of the V transpose, basically you will see it will be V and you will get this as U transpose. Correct? This is what you will get. So what is the SVD of A inverse? SVD of A inverse is basically this particular matrix, right? So whatever you see on the right hand side, this is the SVD of A inverse. But the only thing now that we have to be careful about is the following. So in this particular case, in this particular SVD of A, we know that sigma 1 is greater than or equal to sigma 2 is greater than or equal to sigma n is strictly greater than 0. Is that right? That is what we have. But now here, because of this relationship, you see that 1 upon sigma 1 is less than or equal to 1 upon sigma 2 is less than or equal to 1 upon sigma n, and these are strictly greater than 0. Do you agree?
Yes, sir.
So you had this as your dominant singular value here, and the first column of U and first row of V to be the corresponding singular vectors corresponding to the dominant singular value sigma 1. Now the dominant singular value is 1 upon sigma 1 in A inverse. That's the only difference. So the last column of V and the last row of U transpose actually are the corresponding singular vectors with the dominant singular value 1 upon sigma n for A inverse, right? The role of right and left singular vectors also change. So here you have U and V transpose, here you have V and U transpose, right? So the roles of right and left singular value vectors also has changed, and the ordering of the singular value is exactly the opposite by taking A inverse. But that's all. This is all you have. And now I can generalize this concept. I can generalize this concept to the case when suppose A is a tall matrix. Okay, suppose A is a tall matrix. It's M by N and M is greater than N, and we will assume that rank of A is equal to N, which means that columns of A are linearly independent. Okay. Columns of A are linearly independent. If that is what we have, then let us assume that A is equal to U sigma V transpose. Okay, so you have this matrix U, and then you have sigma 1 up to sigma n. This is 0. This is your matrix sigma, and this is your V transpose, right? So this is how your matrix A looks like. Correct. So size of A is M by N. So size of sigma is also M by N. So if A is tall matrix, sigma is also tall matrix, and you have this type of arrangement in your sigma matrix, right? So this is your sigma matrix. And now what is A transpose? A transpose is V transpose sigma transpose U. So you have V transpose and sigma transpose. How does it look like? It is an N cross M matrix with sigma 1, sigma 2 up to sigma n sitting here, and then the 0 will go here and you will have a U here, right? So A transpose A inverse A transpose. Okay, if you want to find this particular thing out, what will you really have? So you have A transpose A. So you have V transpose sigma transpose U. That is your A transpose. A is U sigma V transpose, right? I haven't made a mistake. So you have U sigma V transpose, V sigma transpose, U transpose. Here I have made a mistake, right? I should have V. Is that correct? So this is for A transpose. Then A is U sigma V transpose. A transpose A will take inverse of this and A transpose. What is A transpose again? V sigma transpose U transpose, right? So you simplify this. So U transpose U is identity. Sigma transpose sigma is basically the square matrix with sigma 1 square, sigma 2 square, sigma n square here. You have inverse. So when you take inverse and V sigma V transpose, so V transpose inverse, so you'll get V sigma square. So 1 upon sigma 1 square up to 1 upon sigma n square. That is what you will get for the inverse V transpose V sigma transpose U transpose, right? So this is what you will get. So V transpose V is again identity. Sigma transpose is basically the wide matrix with sigma 1, sigma 2. So basically, if you simplify this further, then what is A transpose A inverse A transpose, which is nothing but the pseudo inverse. Okay, this is the matrix that I really wanted. So this is the generalization of this pseudo inverse. So this will be basically equal to V 1 upon sigma 1 up to 1 upon sigma n, and this 0 and U transpose. Okay, the SVD of this will look like this. I am simplifying this further. So 1 upon sigma 1 square multiplied by sigma 1 will give you 1 upon sigma 1 and so on and so forth, right? So this will be what you will get. This looks almost exactly same as this particular matrix A inverse singular value decomposition, right? So that's why this pseudo inverse is kind of called generalization of this is called as generalization of inverse of a matrix. Okay, so this is what pseudo inverse, and this is how SVD can help you compute the pseudo inverses and so on and so forth. Okay, so once you know the SVD of matrix A, you don't need to do A transpose A inverse A transpose. You just rearrange the vectors, singular vectors and singular values in this way, and this particular matrix that you see here is actually the pseudo inverse of given matrix A. Is that okay, Kaushik?
Yes, sir. So just one question. If you go back,
Yeah.
One page. Yeah. So, sir, here,
Yeah.
in the last step,
Yeah.
inverse of V transpose, I guess V is not a square matrix, right? So,
No, it will be a
inverse,
square matrix, no?
sir, we have the 0 also. I mean,
Where? No, the
okay.
zero is present in sigma. V and U we have considered to be square matrices.
Yes, 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 sir. Yes,
Yeah.
sir. It's fine. Yeah, yeah.
Yeah.
Thank you.
Is that okay?
Yes, sir. It's fine.
Yeah.
Thank you, sir.
Yeah. So this is the relationship of singular value with pseudo inverses. But one comment I want to make once again, it's like a passing comment, but you should remember is that even if this pseudo inverse can be represented very easily using singular value decomposition, actually computing singular value decomposition for large matrices itself is a very challenging task. Okay, because singular value computation is not an easy thing to do. You have to use iterative algorithms. Basically, you have to convert the problem to the problem of computing eigenvalues and eigenvectors of A transpose A and AA transpose. Okay, so this problem is computationally not really very easy. Like SVD computation takes really long time for very large matrices, which you can easily encounter in your real life data sets. So in general, when you have need to compute pseudo inverse, people never compute pseudo inverse using SVD. They always use Newton like iterative algorithms. Okay, so there are certain iterative algorithms that people use, and using those algorithms people actually compute pseudo inverse. Okay, so I think one of the assignment problems in assignment 2 there was a problem that you had solved. I did I give that assignment problem to you where least square solution was to be computed iteratively? Was that problem there in assignment 2?
Yes, sir. But it
Yeah.
was not conversing.
Yeah, correct. So the iterative way of solving that least squares problem actually so that iterative way basically was dependent on computing pseudo inverse of a matrix iteratively. Okay, the iterations are designed in such a way that the pseudo inverse of a given matrix actually gets computed iteratively, and the pseudo inverse actually exists because we had that condition that the columns of the given matrix were linearly independent. Okay, so that was something that was important. So I think I probably did not mention this in the question itself, but now I'm mentioning it that this method of iterative solution basically depends on the idea of computing pseudo inverse of the matrix iteratively. Okay, so in general, in real life applications, many places you will realize that SVD is avoided. Okay, computation of SVD is avoided if you are interested in computing pseudo inverse directly. Like if you want to solve least squares problems and all, for a very large data set. Typically, SVD, though you have a closed form solution, you will not actually look at this closed form. So you will not compute SVD. You will compute these pseudo inverses in iterative way. Okay, that is something that is important. It's just a comment in passing. Possibly you will use softwares and things where inherently they will do all these things, and you may not need to know, but this is just a comment that I wanted to make. Okay, anything else?
Sir, just one associated thing, one last.
Yeah.
How is the Penrose inverse calculated?
So in an iterative fashion. So Penrose inverse, Moore-Penrose inverse is basically this pseudo inverse. So if one of the singular values is 0, like you do not have this condition of what you call full rank property, right? So here also, if one of the sigma, like sigma n is 0, if your rank is n minus 1, you still can compute Moore-Penrose inverse using this particular formula that I wrote. So then, like last singular value is 0, so you'll also write 0 there. That's it. So 0, you'll not do 1 by 0. You'll just continue to use 0 as 0, and all other non-zero singular values you'll take inverses, like the one that you see in this formula, and you just change the places of v and u, like v and u transpose. Then you'll get that Moore-Penrose pseudo inverse for any arbitrary matrix. So that actually matches with this particular pseudo inverse that I have written if you have full rank property. And any pseudo inverse that you have like heard of, typically, though they can be like this Moore-Penrose pseudo inverse, they can be done through SVD closed form. Typically in real life, they are actually computed using iterative methods.
Okay, thank you, sir.
Yeah. Okay, anything else you would like to say or would like to add?
Sir, like it's
Yes.
not related to the current topic, but like you asked us to find out like way back in the course that how are the polynomial roots of like how are the roots of a like a polynomial with degree pi or greater than that calculated in the back end of the computer.
Yeah.
So can you like discuss that?
Yeah, I can discuss that. So let me just see online. So if I can demonstrate that, it will be fun. So let me see if I can open MATLAB and try to do this. So it is done by something which is called as QR algorithm. Okay, so what really happens is that
Sir, can you repeat the question?
Okay, the question that Kshitij asked was like sometime when I was introducing eigenvalues and eigenvectors, we all realized that eigenvalues are basically roots of characteristic polynomial, right? So if you want to compute eigenvalues, you find out the characteristic polynomial by writing determinant of a minus lambda is equal to 0 and solve this characteristic polynomial for lambda. In other words, compute the roots of this characteristic polynomial. But in mathematics, two great mathematicians, Galois and Abel. Okay, so the first Abel and then Galois. These two mathematicians actually about 200 years ago now proved that beyond degree 5, beyond degree 4, basically greater than or equal to degree 5, you cannot have a closed form formula in terms of those square roots or radicals to express the roots. Like if you have a quadratic polynomial, you can write down the formula minus b plus minus root b square minus 4ac divided by 2a. This is formula that probably everybody from our school days knows, how to compute roots of a quadratic. So like that, you can have formula for degree 3, degree 4, but degree 5 onwards, such formulae do not exist. Mathematically, it is proven that there will not be a formula which will give you roots in closed form using these radical signs. Okay, so that tells us that if you want to find out eigenvalues of a matrix whose size is greater than 5, And easily all the real life applications with which we work, the thing is that it will always have size greater than 5. So you'll have like many eigenvalues to compute, but you will not have a formula to compute those eigenvalues. So basically the problem is how do you compute eigenvalues? So the answer was you find out roots of characteristic polynomial. But the problem now is that roots of characteristic polynomials cannot be computed easily. Roots of characteristic polynomials cannot be computed easily if you have characteristic polynomial greater than 5. So you have to resort to the numerical methods. So what actually happens and what people really use in the back end is that the problem is looked the other way around. So when people want to find out roots of a polynomial, actually they construct a matrix. They construct a matrix whose characteristic polynomial would be the polynomial whose roots you wanted to find out. And then they compute the eigenvalues of that matrix. Once you compute the eigenvalues of that matrix, then you have found out the roots of the characteristic polynomial. Does that answer your question, Kshitish?
Yes, sir.
So in real life, what really happens is that people actually convert the polynomial problem into linear algebra problem. So the numerical problem of computing roots of the polynomial actually is converted to the linear algebra problem of computing eigenvalues of a matrix, and they actually compute eigenvalues of the matrix using numerical algorithms to compute eigenvalues. So the power of these algorithms that are there in linear algebra, they actually give all eigenvalues in one go. Like one method we saw in the class, I remember I was discussing, was power method, where you would converge the iterations to the dominant eigenvalue and dominant eigenvector, right? So there are better methods called as QR algorithm. So this QR algorithm, not to be confused with QR decomposition or QR factorization that we have seen. So this QR algorithm to compute eigenvalues and eigenvectors actually basically gives all the eigenvalues in one go. That's what really happens. Okay, so in order to compute roots of polynomial, they actually use linear algebra techniques. So that's something that is very interesting that many people do not know. And because we have been seeing eigenvalues, eigenvectors for so long, probably from first year courses in mathematics that you have taken, from that level 12+1 level, everybody is seeing eigenvalues, eigenvectors. It's like imprinted on our mind. Whenever we say eigenvalues, we'll say construct characteristic polynomial, find roots. It never occurs to us that finding roots of polynomial probably might be a very difficult problem, and indeed that is the case. And actually eigenvalues are never computed by finding roots of the polynomial. In fact, roots of the polynomial are computed as eigenvalues of an associated matrix whose characteristic polynomial is that polynomial. Is that okay? So Kshitish, like all your first year course algorithms, numerical techniques that you would have seen, like bisection method, golden ratio search, regular falsy, and what those secant methods and all those things, which give only one root, Newton's method, for example, they will all give one root at a time. They are not ever employed in computing roots of a polynomial. Okay.
Yes, sir.
Yeah.
Sir, so from the characteristic equation, we reconstruct the A matrix, like
No,
the
so you have to construct a matrix A. You have to construct a matrix A, which will have that given polynomial as its characteristic polynomial. So there are several ways in which you can construct a matrix A. There will be many, in fact, infinitely many matrices whose characteristic polynomial will be the polynomial whose roots you want to find out. So people use interesting forms like controller canonical forms or observable canonical forms. So there are canonical forms. So canonical form meaning special matrices which are constructed, and those special matrices are constructed in such a way that computation of eigenvalues is computationally efficient. Amongst all the infinitely many matrices, you will pick that matrix which will be numerically better. Okay, so that's what people will do. Is that okay, Pratyush?
Yes, sir.
Yeah, so these are like all these type of things that you are asking. So these things are very standard things and they are covered in that computational linear algebra course. Okay, so I'm kind of advertising. So these are the type of things that we will discuss in the computational linear algebra course that I will offer next semester. So these are very nicely in detailed discussed in that course. These things. And again, like these are very standard things, so you can find these things in those popular textbooks which I keep mentioning. Golub Van Loon's book on matrix computations, or David Watkins' books, Fundamentals of Matrix Computations. These books have these things explained very nicely, beautifully explained. So if you are interested, you can go and check those books and see. Okay,
Hello,
any
sir.
other? Yeah.
Sir, I have a question. I share in chat box at PC.
Chat box. You can ask it, no? Like chat box. I cannot see it. Huh. The tall matrix rank is, and then how can we find out un plus 1 and so on till um? So those vectors you can find out by completing the orthonormal basis. So up to n, you have those n vectors that are determined by the action of A. After n, from n plus 1 to m, you have that m minus n dimensional subspace at your disposal. In that m minus 1 dimensional subspace, you can complete the basis. So you have u1, u2 up to un, the orthogonal vectors determined by A. Then un plus 1 up to um, you can complete this basis into an orthonormal basis, so that you are free to choose. You can choose any.
But sir, it is arbitrary, but we cannot find sigma n plus 1,
They're
and
all
so
zero
on.
anyway. They're all zero, na? Those singular values are anyway zero. So whatever you,
1 by 0 is not defined, sir.
what?
1 by 0 is not defined.
What is not different?
Because of the un, if I write 1 by sigma n something, so this is not defined. So un plus 1, un plus 2 are arbitrary, I think, sir.
Arbitrary, but they have to be orthogonal, na? So you have to complete it into an orthogonal basis. That how do you complete into an orthogonal basis? It's up to you. That's arbitrary. But it has to be an orthogonal basis. U matrix has to be an orthogonal matrix, right?
Yes, sir.
Does that answer your question?
But sir, have you any particular method to find, sir?
No. There are many methods, but yeah, no particular method. Typically, those singular values, those singular vectors are also not important. Typically, those singular vectors are never computed in real life applications.
If I calculate them manually, then it's difficult to find the all un. So sir, if any question in exam, then how it can handle, sir?
What? I did not follow. No, you did what you cannot handle. I did not understand.
Sir, if it have no any particular method, then sir, if any exam question
Okay,
find the
you are
all
worried
un.
about exam. I am telling you in exam, I will not ask this. Okay, don't worry. In real life, how do you do these things? They are difficult. In exam, I will not ask this thing. I may ask some other thing in exam, not this thing. Okay. So even if this thing is asked in exam, you can just observe up to 3-dimensional geometry. You can observe and orally you can tell what is happening. In exam, like all exam problems that you will see, it will all be oral calculation. At most, some slight calculations you'll have to do with pen and paper. You don't even need calculator for those type of calculations. Like if you want to save time, then you will do oral calculations quickly. So all the calculations and everything that you will need in exam, you can do very easily. No worries. Okay.
Okay, sir. Thank you.
Okay, if there is any other question. Okay. So do you have, okay, let me stop the recording.